3, 2, 1.
Space Nuts.
Thank you for joining us. And once in a while, we like to send a shout out to our patrons and thank them for putting a little bit of their money into this program so that we can keep operating. And we've got a few patrons that have signed up recently. One of the benefits of being a patron is that we name you, but we don't shame you. We thank you. And one of those is Shane. We don't have a surname for Shane, but Shane will know who Shane is. Derek Fox, Nige Gardner, and Ashley Exetel, who have all signed up to be patrons. Ashley is actually signed up to the highest level as a patron. So thank you so much for putting your support behind us and having faith in us. We certainly appreciate it. So a salute to you. And of course, if you'd like to become a patron, you can do that on our website. Just go to spacenuts.io or spacenutspodcast.com. Click on the supporter link and all the options are there. Patreon, PayPal, Supercast, whatever suits you. Of course, as I've always said, it's not mandatory, but there are growing benefits to becoming a patron, which we'll be able to tell you about in the not too distant future. Now, Fred, let's move on to our next question. Now, first up, apologies for the sound quality, but we'll try and tweak that in the course of post-production.
Hello, Fred, Professor Fred, and Andrew. This is Paul from Philadelphia, USA. And I was wondering, I'd seen something on WIMS, which I believe stands for Warm Hot Interstellar Medium. And I've seen that it accounts for a big chunk of the matter we can't see. And I know it's not a dark matter question, but maybe you could shed some light on that. And also, I'd seen that it's actually extremely hot, this matter. But for some reason, our infrared satellites can't pick it up. So if you could discuss that and educate us on that, I'd appreciate it. Thanks. Love the show, and it's definitely in the top 2 of all science podcasts that I listen to. Thanks a bunch.
Thank you, Paul. Thanks for the endorsement. Appreciate it. He said maybe we could shed some light on WIMS, the Warm Hot Interstellar Medium, but I think we already shed light in the last segment. So we've already done that. But yes, he's talking about something that's somewhat mysterious, the warm, was it warm hot interstellar medium?
Yeah. Yes. It's technically the warm hot intergalactic medium, because this is what is between the galaxies. And it's really an interesting story, and it's one that's got absolutely direct links with astronomers here in Australia. So, and it's a lovely acronym, isn't it? The WIM, W-H-I-M.
Oh, yeah, it is.
You astronomers, you just have these WIMs and then you just get on with it. Yeah. Anyway, so what is it? It's something that is predicted by cosmological models. When you look at the way matter behaves, I'm talking now about on the largest possible scales. We know that the Big Bang generated hydrogen and helium and this stuff called dark matter, and it's not dark matter we're talking about, exactly as the question said. This is real matter, what we in the trade call baryonic matter. Baryons are normal matter. It's atomic nuclei and, just normal stuff. So you're made of baryons, Andrew. You should be called Barry, really, shouldn't you? Anyway.
Yeah, well we all should be then.
Hello, Barry. So this is normal matter that's predicted to exist within the galaxies, but in the space between the galaxies. But the mystery has always been how much of it is there. And people they've looked at the theories for the way the universe was created, the origin of the universe, the Big Bang, and how it behaved after that. And they've worked out that we don't see enough of these baryons. In other words, the amount of normal matter that we see, and it's mostly hydrogen, it is not enough to satisfy the kind of equations that relate to the formation of the universe. There's something missing in our understanding, and it's actually usually called the sometimes called the missing matter problem. But that tends to stray into territory that is occupied by dark matter, which is something completely different. So it's better calling it the missing baryon problem, not the missing Barry problem. That's a different one altogether. The missing Barry.
No, he emailed me yesterday, actually. Yeah.
Should be a series of books called "Where's Barry?" Shouldn't there? That would do it. Yeah. So it's called the missing baryon problem, and there was a really what you might call a pivotal paper that came out last year, which was produced by principally Australian astronomers using the Square Kilometre Array Pathfinder, ASCAP, and our facilities that we have access to in northern Chile, the ESO telescopes, European Southern Observatory. A number of my friends and colleagues were involved with that work, a really important paper which actually won an award. Actually, I beg your pardon, I'm mixing up two papers there. This one didn't win an award. It was...
just wasn't good enough, Fred.
It might still do, actually, because it's an important paper. There's a poignant side to it, though, because the lead author, Jean-Pierre, I think his first name was, we'll all call him JP, Marchand, he was a young bloke. He's in his 30s or 40s. He died 2 weeks after that paper was published. It was a shock to everybody. I think he had a heart attack. Really, really tragic. Yeah.
Wow.
But remarkable work and remarkable piece of astronomy. So what that process did, what this discovery did, and it was all to do, by the way, with fast radio bursts. It allowed the light from fast radio bursts, the radio signals passing through the universe, to essentially be a tracer of what's in the intergalactic space. And sure enough, they found that there was really strong evidence for this WIM, the warm, hot intergalactic medium, at a level of maybe 1 to 10 particles per cubic meter. So it is highly rarefied, but it's hot. And when you're looking at really rarefied media like that, hot has a slightly different connotation. It just means the atoms are moving very quickly, or the particles, the subatomic particles. It doesn't mean that you could, hold out your hands and feel the heat of it. The temperature is up to 10 million degrees. It's somewhere between 100,000 and 10 million degrees. But that is, for something that's so rarefied, all that's telling you is that the individual particles are very energetic. They're moving very fast, and it's the fact that this is such a rarefied medium that explains the other part of the question: why don't we see this in infrared? It's something that's emitting heat, so why don't we see it in the infrared? It's because it is so rarefied. There's so little of it that you don't detect it by normal infrared detectors. So,
well, maybe one day if they, have much better instruments down the track that we haven't been able to invent yet. But,
that's true. But, the technique that has been done to detect it, which is looking at the way fast radio burst signals are modified by, it's actually a process called dispersion. It's the way the short and long radio waves are separated in the same way as a prism breaks up light into its spectrum. This intergalactic medium breaks up radio waves. It slows the long wavelength radio waves down. And so you get the fast radio burst arriving slightly later than with the long wavelength radio waves than the short wavelength radio waves. And that's what tells you there's something there. And by analyzing that, you get this measurement of the WIM. It's a great story. Yeah, I'm sorry I've gone into more detail than I intended to, but there you go. It's just too good a story to miss, and a great question.
Yeah, wonderful. Thank you, Paul, and hope all is well in Philadelphia. Let's move on to our next question from Martin.
Hello, Space Nuts. Martin Berman Gorvine, science fiction writer and newly faithful listener here, with a couple of completely off-the-wall questions about the, as far as we know, non-existent luminiferous ether. if it did exist, how would astronomy be different, as this would presumably affect the entire spectrum, visible light, radiation, gamma rays, radio, everything. And could it be somehow be harnessed, the luminiferous ether, that is, for space flight? Love your show. I know this is completely ridiculous and fantasy type of question, but it would make my day if you answered it on your podcast. Thanks, folks.
Lovely to hear from you, Martin. Lovely to hear from a sci-fi writer. And yeah, why not ask us a question that's completely ridiculous? I mean, that's what science fiction is all about sometimes, isn't it? Just to take someone on a wild ride. Why not do it on our program? Non-existent luminiferous ether. Yeah. You better explain that first, Fred.
You should be taking the hint from Martin and building this into your next sci-fi novel, Andrew.
Well, as soon as I figure out what it is, I might.
Well, it's what used to be thought pervaded the universe. So, people in particularly the 19th century, that's when this thinking was at its peak, recognizing that sound waves have to have a medium to travel through, whether it's a piece of wood. If you hammer it at one end, you'll hear it at the other, or whether it's the atmosphere. The atmosphere is what's taking the sound from my voice to the microphone right now, and it's because there is that medium. There is the air there that's transmitting the sound, and it was a natural thing for early thinkers to wonder whether there is a medium which transmits light waves. Once the wave nature of light was recognized, which was pretty well in the actually early years of the 18th century, it was recognized that there's probably a wave nature to light. Maybe a little bit later, Newton thought it was particles, but it was later physicists who worked out that it was waves, actually predominantly at the beginning of the 19th century, and now we know it's both. It's waves and particles, so work that one out. But it's throughout the 19th century, people firmly believed that light was a wave and thought that it might need some medium to transmit it. And that's what the ether was, the luminiferous ether. So it was experiments at the end of the 19th century, the famous Michelson-Morley experiment, that told us that the ether wasn't there. So if you imagine a stationary medium that's transmitting light, the Earth is moving through that medium. If you measured the speed of light in the direction in which the Earth is moving, and then measure it in the opposite direction, they should be different, because we know that Earth's motion is 30 kilometers per second. That's been known since we knew the distance to the sun. That's suggested that there should be a difference in the velocity of light, and it was found by many, many repeated versions of the Michelson-Morley experiment that it's not. It's the same no matter what direction you're moving in, no matter what direction what speed its source is moving at. And that was why the ether was basically discarded as a theory. What came next is really important, because it was on that basis that the whole construct of relativity came about. It's the fact that light travels at a constant speed in a vacuum, and it doesn't need an ether, that allows you to, first of all, work out the special theory of relativity, which says that, okay, light's a constant, therefore time and space must warp, and we know that happens. And then lead on to general relativity. So it was an absolutely pivotal discovery, the constant speed of light. So turning now to Martin's question, had that not been the case, if the ether was real, it would certainly have produced a very different view of the universe. Relativity wouldn't exist, as our modern understanding of the theory of relativity wouldn't exist. And so when you think of all the things that come out of relativity, and in particular general relativity with black holes and, neutron stars and gravitational lensing, all of that stuff, I think I'm right in saying would have been dismantled by the presence of an ether. We might not have had black holes. I'm not sure whether I'm making too strong a leap of deduction there, but it certainly would have scuppered special relativity, the idea of objects moving quickly through space, it would have. This is important, actually. Thinking about it, it would have removed the speed of light as the ultimate speed limit in the universe. So there you go. That's how you do it. That's how you, in science fiction, travel faster than light, because you you introduce the ether.
Look, all right. Yeah. I'll save that one up.
Yeah.
Interesting.
No, very nice question.
All right.
Nice question. Some interesting.
Yeah, wonderful. Thank you, Martin. Lovely to hear from you. And please send me a list of your titles. I'd love to look them up. I might have written a few science fiction books, but I was motivated to do that by reading them. So, I'd love to see your work. I'm sure it's far, far superior to anything I've ever done. But thank you for your question. Greatly appreciated. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.